Hello, somebody. Greetings. Who's ever there? Ellie, I knew it would be you. Okay, but two others are joining you, so let's see who else is here. Glad you can make it. We're going to finish up with the Einstein ideas today and start some Einstein problems. So, who else is there? Try and say hello. Good, good. Hope everybody's doing well, keeping your sanity out there in this crazy time. Another week or so, and yeah, we'll see what they want us to do. We'll be online until the 25th, but then the heads of the Bundesländer are going to meet and decide what to do. Myself, I'm guessing we'll be online until winter break. After winter break, I don't know. I don't know. The numbers came down at least yesterday. I hope they stay down. Sure. And as soon as I know, I'll let you and the group know if anything changes. Okay, let's see if somebody else is out there. I've got Ellie, but I'd like some more. All right. Sure thing. Okay, so I see another person maybe joining us. So say hello if you're there. While you're joining us, I'm just going to say that we're going to finish up with Bohr's correspondence principle. Remember last time we talked about Bohr saying, hey, if an old theory works, then a new theory better incorporate the old theory, okay? Or else we got to throw out the old theory. So to do that, we're going to check three Einstein relativistic equations and see if they still work under Newton's conditions of a low velocity. We're going to do that by putting zero or close to zero in for the velocity and see what happens. I can't remember how far we got, but I don't think we finished this last time. So let's look at the first one. For time, to get relativistic time, we take the original time, or time from somebody in a rest position with respect to the events, divided by this correction, square root of 1 minus b squared over c squared. Good, so we're going to put in 0 there for v. So if I have a fairly low thing, so I get t equals t0 divided by square root of 1 minus, well, 0. And it comes out to just being t0. So Newton would say, yeah, t is just the same as t0. So if you're in low speeds, the times agree with each other. I think we got that last time. Let's continue with length. And length is going to be this. I take the original length as in a rest position. And then to get the length seen by an observer, I got to get this sucker times, you guessed it, square root of 1 minus v squared over c squared. Well, this time I get, if I put in 0 for v squared, I get L equals L0 times the square root of 1 minus 0. Well, that's the square root of 1 is 1. So I get that the length is indeed the same as the original length, which is what we would say under under Newton's ideas, right? It's essentially not much of an equation, but it's an agreement that it does follow Newton's laws. Let's see if that can be a little less blurry there. Hope that's all right. And the third one is for momentum. We kind of did this one already. It's a little longer. It says it's mass times volume divided by the correction square root of 1 minus v squared over c squared. And you guessed it, Chester, we're going to do the same thing. Essentially, if I keep it as a non-zero number, I still get mv on top, but the bottom of the fraction gets really close to 1 minus 0 under a square root. So that in effect, the Newton equation is what we end up with, because I get mv divided by 1, which is just m times v. So in other words, check, check, check. It does correspond with Newton's old laws about physics, about time and distance. Okay, that's the end of what I needed to tell you about Einstein and his many and cool ideas. I want to do a couple examples today with you of using these equations, okay? And then we're going to give you an assignment and have you work on that more or less the rest of the week. So that's the scoop, okay? And I'll tell you more about that assignment towards the end of this period. Exactly. So these work if the velocity is 0, Ellie, or really close to 0. Then essentially Einstein's relativistic equations, it's like this little 1 minus square root of e squared over c squared under the square root. This whole thing, this thing is a correction. So the correction ends up being 1, 1, 1, whenever the velocity is 0 or close to 0. And then we enter a Newton world, which is the world we really know most of the time. Okay, anything else before we continue? I guess I'll say Ellie from you because you're the only one. But only, yeah, exactly. Yeah, okay, all right. Then I'm going to erase this. The others will have to see it on video. And I don't know where they are. It's unusual. Usually you guys are all there. Don't know. Okay, so now let's do some, I'll call it Einstein problems. Okie doke. Let's begin with an important one, which is using the time equation. Okay, and it goes like this. Here, I marked the page. I'm going to do one with Superman just because I'm an old fuddy-duddy and I know Superman from when I was growing up. Okay, but it could be Superwoman too. It doesn't really matter to me. Okay, so here we go. Superman leaves Earth at 0.7 times the speed of, let's make it 0.70 to get sig figs, times the speed of light. So he's going to go 70% of the speed of light. What page is this on? You know what? It's a book you don't have, Ellie. So I can't give you a page, but thank you for asking. So Superman leaves Earth at 0.70 C to, let's say, repair a satellite. Everybody needs a job. He reaches the satellite in 20.0 hours. Okay, and this part's important. According to his wristwatch. How much time passes on Earth at his base station? At the base station. So we got two different times, okay? We got one with exactly, so two different frame of reference. Yeah, so the frame of reference versus that of Earth, exactly, Ellie. Now, here's the deal. According to his wristwatch, well, let's write the equation down, and then we can think about what's what. Okay, so the equation is time equals T0 divided by this correction again. I always look because I don't want to write it wrong. Square root of 1 minus b squared over c squared. Okay. Because it's according to his wristwatch, okay, let's write these here. I know I'm not being clear, Ellie. Okay, so t is equal to the, I'm going to call it relativistic time. T0 equals time at rest. And this is important with respect to events. Now, here's the tricky part of this. And this is the question I got for you, Ellie. Which t is the 20 hours? Where do I put the 20 hours? Is it the relativistic time or is it the time at rest with respect to the events? How about I take a guess? You got a 50-50 shot. More if you read what I underlined. Is it T0? Yes, it is. So it's hard, but because he's flying and looking at his wrist, look at a watch right there. So he's flying and looking at that. So according to him, this wristwatch value is the at rest value. So that really is T0. So yes, good guess, Ellie. So T is going to equal to T0 I want to make sure I get the answer the book does with this. Hope I don't screw it up. This doesn't look right. Oh no, it is right. It is right. Because we got to do this, right? So it's T0, so 20 hours, or 20.0 hours for rounding. Divided by, now here's Ellie where I'm going to make a suggestion, okay? Go like this. 1 minus, keep it as V. Don't like change it to some other number. Keep it as 0.70 C, and then square that sucker. Divided by C squared. And we're going to continue up at the top here because I know it's probably hard to read. So I got 20 hours divided by 1 minus, divided by the square root of 1 minus 0.7 C quantity squared divided by C squared. Okay, so let's go to the top now. Okay, so what does that mean? I got 20.0 hours divided by square root of 1 minus, okay, so 0.7 times 0.7. Exactly. Yeah, don't do that. Right, exactly, Ellie. So we're going to leave it as 0.49, right? 0.7 times 0.7 is 0.49 C squared divided by C squared. And Ellie, what do the C squareds do? They cancel. Thank you very much. So I got to take the square root of 1 minus 0.49, which of course is 0.51, and I'm sure you know that anyway. And Ellie, if you got a calculator, you want to punch that out and see what you get. 20 divided by 0.51 square root, and let's see if we match what the book gets. I hope. And then you can round it as well as you see fit. While you're doing that, I'm going to erase some of this other stuff. Finish this. Ta-da! Thank you, Ellie. That's correct. It's not only the right answer, but it kind of makes sense. So to the folks back home that are not moving 0.7C, it's taken more time. So even though we measure it with his watch, it's still showing that the movement causes the time to pass more slowly back on Earth. So back on Earth, 28 hours have gone by instead of 20, which is kind of cool. Okay, let's do another one, unless you've got a question, but I think you're doing well here. I just want to do one more, actually. And the other one I want to do is with your new car. Okay, so here we go. Ellie's new sports car is, it's really long. Sorry about that. 15.0 meters long and goes half the speed of light, so 0.500 C. So your car is fast. Yeah, it's like you got a really fast stretch limousine, right? Exactly. Good. So the question, of course, is how wide or how long does car look to folks at JFKS as you drive by with sunglasses on. I'll leave that on. As you drive by. I love it. Okay, so here's our equation. So to get the length, we need the original length times the square root, our correction, of 1 minus b squared over c squared. I'll be honest, the length ones are a lot easier to solve. So our original length is going to be, so L0 is going to be how much? Thank you very much. So we got the 15-meter LA limo, and that's L0 times the square root, our correction, 1 minus 0.500, 0.50 quantity of C, quantity squared, divided by C squared. Man, I hate writing down at the bottom of that board. So we're going to put it up over here, the rest of it. Okay, so here we go. I got L equals 15.0 meters times the square root of 1 minus. And this ends up being 0.5 times 0.5 would be 0.25, right? 0.25, probably O to keep the sig figs. C squared and over C squared. And of course, the beautiful thing is the C's cancel. I love it. And you knew that last time, Alice, so I don't have to ask you again. So let's do this then. So it's 15.0 meters times the correction. So 1 minus 0.25 would be square root of 0.750. Okay, and Ellie, I will let you punch that out, and let's see if we agree with what the book got for what happens to your stretch limousine as you cruise by the school. Congratulations, by the way. That's a beautiful looking new car. Super. Ta-da! Dynamite. Good. Ellie, I'm going to just tell you about the worksheet, and I'm going to tell everybody else as well, but I want to hold it up and show you some stuff. So I'm going to send you this digitally. I scanned it yesterday. I'll give you guys lots of time to do it. But I want to tell you some stuff, okay? So some of the problems are going to be Newton, and that means pretty easy. I can do it like we did our activity with the when we were still in school, where we were meeting and going either together or and guessing our meters per second velocity based on the movement of each person and one person looking at the other. Okay, so the Newton ones are pretty straightforward, and I'll tell you which ones those are. Okay, basically the first two, and then it's B1 as well. But okay, the other ones all involve the Newton equations that you and I have looked at, and then the others will have to see the video and kind of learn how to do them. Okay, but I think you're going to have good success for these. And what I'll do is I got to look at my schedule. Here, let's see when I was going to meet you again. Hold on. In other words, when I'll do another live stream with you. Okay. All right, physics. Here we go. Okay, so I'm meeting you today. Today's Tuesday, and I'm going to meet you Thursday. and that's it. And I'll meet you Thursday at the regular class period time, but maybe not for so long, maybe an hour max, or maybe less than that. I'll take any questions you have on the Einstein problems, and then we may do some new material at that point, but only if I got more than half of you there. I want at least 3 of you there for starting that new stuff. And that will be back in the book, and so I can give you a reference. So other than that, I'll just wish you a good rest of your day, and I'll send everything to all of you, Ellie. Thanks for showing up. Thanks for participating. Power to the people. Stay healthy. See you on Thursday. So not on Friday, exactly. So we won't meet Friday. We'll just meet Thursday. I think that's enough because I'm giving you an assignment to do as well. Good. Okay. Bye.